Hello everybody, this is Dr. Pennington once again, and in this video I'm going to focus on the concept of the redox reaction. This video is actually a video to watch after the assigning oxidation states video, which hopefully you've watched before. That was a precursor to being able to do this one. So if you haven't watched that video, make sure you watch it, because in order to watch this video and see and understand what's going on, you have to know about how to assign oxidation states, alright? Because that's the main thing we're going to be doing here, and if you don't know how to do it, well, you're going to have a hard time. Alright, so let's begin. Let's talk about redox reactions. Now, what does redox actually mean? Well, I'm sure from what you've read, you will know that redox involves a species being oxidized and the species being reduced. Really, redox means reduction, oxidation, reactions where something gets reduced and something gets oxidized. All right. Oxidation means something's losing electrons. Reduction means something is gaining electrons. There's a simple mnemonic here that you can use to try and remember exactly what's happening. All right. This is a mnemonic that I learned in high school back in England. It's one of the very few things I actually remember. For some reason, it stuck with me over all these years, and I'm going to write it out now. The mnemonic is oil rig. For whatever reason, it just stuck in my head, and hopefully it's going to stick in yours too. The idea being that oxidation is loss. This means loss of electrons. Reduction is gain, again, of electrons. Alright, so if we were to look at, say for example, sodium, going to sodium plus and 1 electron. This means this sodium has lost an electron because it came out here. The sodium was oxidized. This is an oxidation. This species was oxidized. We're only concerned about the starting materials. We aren't concerned about the products in terms of what was oxidized, what was reduced. Chlorine, on the other hand, hang on a minute. So sodium was oxidized because it lost an electron. Originally this had a bunch of electrons in it, and over on the other side it's got one less. So it lost an electron. Some species, on the other hand, can gain electrons. Alright? Because electrons are negatively charged, if you lose one, what you end up with is positively charged. If you start off with something neutral that gains a negative charge, it's going to be overall negative. And that is reduction. Alright? Again, we're only concerned about the starting materials in terms of what's oxidized and reduced. Okay, now let's take a look at this reaction right here. I don't want to focus too much on the electrons at this point. I just want you guys to understand what's happened to the oxidation states. All right. In fact, let me just do one more thing. The oxidation state of the sodium here is 0. Just as the oxidation state of chlorine here is 0. The oxidation state of the sodium here is +1. Just as the oxidation state of the chlorine is -1. Oh, sorry. Let me try and draw a negative sign properly. So the oxidation state of that chlorine is -1. So if your oxidation state increases, oxidation is happening. If it decreases, reduction is happening. All right. So with that in mind, what we're going to look at is an example of a reaction. And so what we want to ask ourselves is, first of all, is this a redox reaction? If so, what element's being reduced? What element is being oxidized? And we're going to ask ourselves one more question at the end as well. Until you've done this a few times, there is no way to tell just by looking at a reaction to see if it's a redox reaction. We have to go through a series of steps to figure it out. Once you have done a few, though, you realize actually there are some shortcuts that will enable you to tell if it's a redox reaction or not. The key here is to look for the oxidation states of each of your species, each of your elements, I should say. So each of the elements here, we have magnesium, we have oxygen, and we have hydrogen. Alright, so there's only 3 species we're looking at the charges of. We want to see what they are on the left, what they are on the right, and whether or not they change. Now, one of the things that we saw in the assigning oxidation states video was the oxidation state you assign to something when it's by itself and it's got no charge. We always assign an oxidation state of 0 to that. So for the magnesium, this is Mg0. Is there anything else here that's by itself? Oh, yep, hydrogen is by itself as well. So we're going to assign that an oxidation state of 0. And one thing that should give you a sign that something's happening is, here the magnesium's by itself. Here it's not. Because the magnesium is with something else, it's going to have a charge other than 0. And because the hydrogen's 0 here, and when it's with something else here, it's going to have an oxidation state of something other than 0. So this tells us, first of all, this is going to be a redox reaction. But now we've got to figure out is what's being reduced and what's being oxidized. So we have the oxidation state for the magnesium. Alright, so let's try and figure out the oxidation state of the magnesium here. Well, OH minus is a polyatomic ion. That's called hydroxide, OH minus. And because of that, if we look at how many hydroxides we have 2 hydroxides, both coming from the fact that oxygen's 2 minus, hydrogen's 1 plus, given an overall of 1 minus. If we have 2 of those, then the overall negative charge for those 2 hydroxides is 2 minus. So therefore, can you guys tell what the charge on the magnesium must be? Because this is overall neutral. Well, the charge for the magnesium must be 2 plus. So one thing you should be able to tell is 0 and 2 plus, those are not the same. Something has happened going from here to here. Either the magnesium has lost electrons or it's gained electrons. All right. Which of these 2 does the case for the magnesium look closest to? Well, it's this one up here. The magnesium went from being 0 to being positive. In fact, that's the one thing you'll see about metals. Metals only ever lose electrons. They only ever get oxidized when they start off by themselves. It's always the way. So that means the magnesium lost how many electrons? Well, it lost 2 electrons. But more importantly, the magnesium was oxidized. Alright? And if the magnesium was oxidized, that means something else here must have been reduced. Alright? Now, in water, the oxidation state of oxygen is -2. We'd said before the oxidation state of the O in OH minus is also -2. So notice for oxygen nothing has changed. The oxidation state of hydrogen here is +1. In water it's also +1, which means there's no change there as well. But, so we have the oxidation state of +1 for hydrogen here. But notice we have the oxidation state of hydrogen here as being 0. So what's happened is, when we go from here to here, the hydrogen's oxidation state has decreased. It's gone from +1 to 0, so it's gained an electron. More importantly, it's been reduced. Alright? One thing to always make sure you understand is that you have oxidation and reduction happening in the same equation. You can't have oxidation happening twice or reduction happening twice. So, if we ask ourselves, what species is being reduced? Well, the species being reduced is the water. Specifically, the element being reduced is the hydrogen. So the hydrogen in the water is reduced. The magnesium is by itself, so it's not in anything. The magnesium is oxidized. Alright? And that is the way to figure out about what's reduced and what's oxidized. Now let's just do another one of these, because this may take some time for you guys to grasp. Let's look at another reaction. We have 2 things happening. Zinc going to zinc 2+, Fe2+ going to Fe. Let's fill in the charges as we can see them. Now this one's a little less complex than the last one. You remember we said, anytime we have anything by itself, we always assume its oxidation state is 0 unless it has a charge that says otherwise. So for zinc, the charge is 0. For iron, here, the charge is 0. The charge on the iron 2 plus, well, it is of course 2 plus. The charge on the zinc is 2 plus. So let's look at what's happening to the zinc. And then we'll also look at what's happening to the iron. So, can we tell, is this a redox reaction? Well, we're going from 0 to 2 plus, and from 2 plus to 0. The oxidation states are changing, so yes, it's a redox reaction. The zinc, is it gaining or losing electrons? Remember, electrons have a negative charge, so if this was gaining electrons, it would become negative. And we also said electrons only ever lose it, and metals only ever lose electrons, so we're losing 2 electrons here. The zinc is being oxidized. The Fe2 plus, its oxidation state is getting smaller. Alright, it's gaining 2 electrons. It's being reduced. So we can say then the zinc is oxidized and the Fe2 plus is reduced. But let's go one step further. What if I was to ask, which is the oxidizing agent? Which is the reducing agent? Now what that means is, the oxidizing agent is the species that's causing something to get oxidized. The reducing agent is something that's causing reduction to occur. Alright? So the Fe2 plus is being reduced. Therefore, at the same time, it's causing the zinc to be oxidized. The zinc is being oxidized, and at the same time, it's causing the Fe2 plus to be reduced. So, can you guys come up with what this all means? The species that is oxidized is assigned as the reducing agent. And the species that's reduced is assigned the oxidizing agent. And that's always the case. Alright, no exceptions. Alright, one more. One more. Ah, there we go. Alright, now this one is a little bit more complicated. But let's see if we can figure anything out from the beginning. If you just take a look at this reaction, is there any one element that you think stands out as for sure changing its oxidation state over the course of the reaction? There is only one element that should stand out. And the key is to look for anything that's by itself. Because if it's by itself on one side and not by itself on the other, that's a virtual guarantee its oxidation state is changing. The only one that's by itself here is the tin. Therefore, the oxidation state for the tin is 0. Now, for the tin over on the other side, let's just look at the oxidation state. The oxidation state of oxygen, we know, is O2 minus from what we've seen before. Therefore, a total negative charge of 4 minus for the 2 oxygens. Therefore, the total positive charge on the tin must be 4 plus. So, hopefully you guys can tell that something has happened to the tin. And not just something, we can tell what's happened to the tin. Has the tin lost or gained electrons? Well, it's gone from 0 to plus 4. It's lost electrons, plus it's a metal, so we expect it to lose electrons. And it's lost 4 electrons. Now, the number of electrons at this point doesn't matter. The fact that it has lost electrons is what's important. That means it's been oxidized. So we can say the tin has been oxidized. But now we've got to figure out between the hydrogen, oxygen, and the other element present, nitrogen, which has been reduced. Well, do we have any other elements by themselves? No, no, no. Pretty much the only time you're going to see oxygen or hydrogen being reduced is when you see O2 or H2, as you did here, on the product side of the equation, or the reactant side. If you have a choice of several elements in terms of which is reduced, and you have hydrogen and oxygen as 2 of your options, these will usually not be the ones reduced. It's usually going to be the other species. Alright? However, that's not always the case. Let's just check. Alright? let's look at the hydrogen. This is nitric acid. Let's look at all the oxidation states. All right. Oxygen, we know, in all cases has a charge of 2 minus. So the total charge here for the 3 oxygens is 6 minus. Hydrogen has a charge of +1. All right, so we've got that +1 there. So therefore the charge on the nitrogen must be +5. Let's go over here. Oxygen, once again, has a charge of -2. Because there's 2 oxygen there, that gives us a total negative charge of 4 minus. Meaning the charge on the nitrogen in this case must be +4. Now you can already notice a difference, +5 and +4. But let's just check. We know in water, like we saw before, in water the oxygen and hydrogen have their standard oxidation states, -2 and +1. So therefore that means that this is the reaction that accounts for the reduction. Or at least that's what we hope, unless we've done something wrong. But let's check. Here our oxidation number increased. Oxidation. Here our oxidation number decreased, which corresponds to reduction. In fact, we lost 1 electron, or we gained 1 electron, I'm sorry. Again, the number of electrons gained or lost is unimportant at this point. So that means the nitrogen in the HNO3 is reduced. All right. If you were to then be asked which is the oxidizing agent, which is the reducing agent, of course this guy, because it's reduced, it's the oxidizing agent. This guy is oxidized, it's the reducing agent. And that is how you can recognize and understand redox reactions. All right, thank you.